So, in today's session, we will be looking a little into the introduction to NLP, where it's used, what it is, and two of the most fundamental processes in NLP. One is text pre-processing, why we do it, how we do it, and the other being text vectorization. We'll be implementing a very simple algorithm for text vectorization, and this is known as bag of words. Okay. So, what is NLP? Does anybody have any idea what NLP may mean? Any vague idea? Also, just don't be afraid to like unmute and talk, okay? So we're all like friends over here, so don't be too shy or afraid to talk. So yeah, does anybody have any idea what NLP might mean? Natural language processing.
Well, I've seen it in a few calendar apps where like you can type in, I have to attend this meeting at 6 p.m. So then it can automatically, add the time feature, using normal English phrases.
Yeah, that's actually a really nice example that does use NLP. So yeah, that's a pretty good example. Okay, so in a more like definition kind of way, NLP is that field of artificial intelligence that is concerned with trying to make a computer understand the languages that a human typically speaks. It can be English, it can be other languages as well. So most of the raw data that you get in textual form, it's expressed in some kind of natural language, either in English or in Chinese or any other language that humans speak. But a computer obviously cannot understand all of these languages, right? So NLP is that domain that deals with trying to make computers gain some insights from some kind of raw text data that we provide it. Um, so we have all encountered NLP in some form or another in our everyday lives, knowingly or unknowingly. So, like one of you was telling, the calendar app, it's actually a great example. So, you just type in whatever you want, schedule stuff, and it can put it in the calendar. Does anybody else want to try and name any other application that you feel might use NLP? Anyone else?
Or maybe like Siri or Alexa and stuff like that, but that's a similar example.
Yeah, that's a very nice example actually, because that's exactly what I had in mind as well. So
Right.
Siri, Alexa, Google Assistant, all of these use NLP pretty heavily. Chatbots is arguably the most popular of NLP applications. So yeah, that's a great example. And also the autocorrect, autocomplete that your keyboards keep doing, that's also an application of NLP that we unknowingly or knowingly use in our daily lives. And these are not all, these are just two examples. There are quite a lot of fields or applications that use NLP. So, yeah, we can sort of divide NLP based on what kind of methodology we use while trying to do NLP. So, based on what method we use, we can classify it as rule based, statistical, or neural. So, rule based, if I have to talk about rule based, assume you have a word that is in its present continuous form. That means it ends with ing, right? And now I want to convert it back to its root form. I can sit and write rules to convert words in other tenses back to their rule forms. Like if it's ending with ing, I can be like subtract or remove this ing to make it root form. If it's ending in ed, remove this ed to make it in to its root form. So all of these are like hard coded rules, right? To change a word that's not in its root form back to its root form. So that is the most primitive form of NLP, the oldest form of NLP. That's rule-based NLP. The second type of NLP is statistical. Statistical, obviously, as the name suggests, uses statistics and probability to go about modeling languages. One of the examples being Markov chains. I'll not go into too much detail about Markov chains in this session, but yeah, statistical methods basically. It can also be as something as simple as calculating frequency, mean frequency, stuff like that. Neural is, like the name suggests, using neural networks. Um, in this or in one of our sessions for NLP rather, we will be looking at a kind of technique that uses neural networks that's specifically called word to vec. It's used for text vectorization to convert something that's in words to numbers. So word to vec uses neural networks. We might also look into other neural network architectures to perform more NLP tasks, but that's more about that later. Now we'll be sticking to statistical mostly, and NLP can also be divided into two, like NLU and NLG. So NLU stands for Natural Language Understanding and NLG stands for Natural Language Generation. So natural language understanding deals with that part of NLP that is concerned with taking those data in natural language and trying to give some inference about it. One example would be sentiment analysis. So you take in data that's either customer reviews or tweets, and you try to decide whether it's a positive review, a positive tweet, or a negative tweet. So that is, you're trying to understand the language. You're not really generating anything there. Natural language generation deals, as the name suggests, deals with making computers generate the languages that humans speak. An example again would be your chatbots kind of thing. So when you talk to Alexa, she can reply to you in perfect human language, right? So you can understand whatever she says. So she is doing natural language generation in a way, in a manner of speaking. Um, so now let's go over some common tasks that are done in NLP. One of them being sentiment analysis, probably really popular. If you've heard of NLP, you've probably heard of sentiment analysis. It's probably used, or not probably, it's used mostly in customer reviews and stuff like that. So you can use it to say if your customer is happy with your service or not. You can use it to analyze the sentiment or emotion in a piece of text and decide how to respond to that. You can also do that. I've seen like a lot of people do that for tweets, right? So you can decide if a tweet is positive or negative and stuff like that. The second pretty common task that's done in NLP is something called topic modeling. So, what topic modeling is that you're given a bunch of documents and you want to or group these documents based on what topic they're talking about. So, maybe one is talking about animals and another is talking about food. And so, a common example would be like news articles, and you have to group news articles based on what is it that they're talking about. So that comes under the that is something that's called topic modeling. Text classification is basically, if I were to give an example, you probably all heard of spam filter, right? So your mail can be classified as spam or not spam. So that in a way is text classification. You're classifying a mail that's basically text as spam or not spam. That is text classification. So it's pretty commonly used, as you can probably tell. Um, Next is something called as text summarization, and pretty much as the name suggests, you have a very long page of text, not a page, but a very long document of text, and you got to give a summary to it. And you can actually code to make your computer generate the summary instead of doing it by hand or manually or something. Another good example of NLP would be in plagiarism checking. So that basically uses document similarity. So you have like a bunch of documents and you got to decide how similar they are. And based on how similar they are, you can decide if it was plagiarized or something. So document similarity is a pretty important task in NLP. And machine translation is pretty much what your Google Translate does. Give it a sentence or a word in one language and it tries to produce it in another language. Typically, for machine translations, you use neural networks. Neural networks is what is used in most of the NLP tasks these days. but we will talk more about that towards the later sessions, not right now. Question answering is, if you have attended the orientation, you've probably seen the COVID Q&A model that we shown. So you give it a question and you give it a paragraph or a document of text that's called the context. So what your model tries to do is it tries to find the answer to your question in the given context. So that's basically what question answering deals with. All right, so am I going too fast? Should I slow down a bit?
I don't know, it seems fine.
Yeah, cool. Right. So for any NLP task, right, there are like these two steps are pretty fundamental. So you have to do these two steps before you go on to do anything else, like trying to find document similarity or trying to summarize your document. Before you go about doing that, you have to pre-process your text and vectorize your text. So text pre-processing is basically cleaning the text, because not everything that you have in your text might be relevant to what you're trying to do. We will see a case that will make it clearer to you in a while. But yeah, text vectorization, basically, like I was saying, computers cannot really understand the languages that humans speak, right? So we need the data to be in some kind of numerical form. And that's what text vectorization deals with. So it's pretty fundamental if you want to go about doing anything NLP related. You have to first convert all of your text into some kind of numerical form. Right. So what tools do we use for NLP? One of the most commonly used tools is this Python package for NLP. It's called Natural Language Toolkit. It's pretty popular and for pretty good reason too. It has a very wide range of utilities, ranging from tokenizers. I will talk about tokenizers in a while. And it also has a large collection of corpus. Corpus is basically the NLP lingo for a document or text, right? It's not anything fancy. And it also has functions for common NLP tasks. Two functions that I've listed here are named entity recognition and part of speech tagging, rather. So named entity recognition is that function that is concerned with trying to identify each part of your sentence as a name of a place or a name of an organization or whatever it is. Is it a name? Is it a place? Is it a country? What is it? So that is what named entity recognition deals with. Part of speech tagging deals with trying to tell the words in your sentence, if they are verbs, if they are nouns, if they are adjectives, adverbs, what are they? That is what part of speech recognition deals with. So if you're interested to know everything about NLTK, like in depth, I have given the link. This PPT will be shared to you later on. So you can go and check the other functions out. There are a bunch of them. So it's really convenient to use NLTK. So that is what we will be using in a little coding that we'll be doing in today's session. We won't be doing much coding, but we will be doing the essential parts. Okay. So now, starting off with text pre-processing. Why do we have to pre-process our text? So, okay. So you will obviously have a bunch of data, right? So but not always will the data that you have be useful or relevant to whatever you're trying to do. It holds good for any other task, not just NLP. You probably won't use all the data that you have before cleaning it, anyways. So, if I were to give an example, you're trying to analyze something in a tweet. You're trying to analyze the emotion in a tweet. You're trying to do sentiment analysis. You do not need the username or any URLs that might be in the tweet along with what the person is actually saying. So you would do well to just rather remove all of those things before you feed that into any other algorithm. Because usually when we vectorize text, we put it in a form of a matrix and we map every word to either a vector or its frequency, or so you map every word to a number. And when you have like really large amount of data, you'll be spending too much memory if you decide to map each and every word that you have to a number or a vector. So it would be better for you to sort of see what kinds of words are relevant to your task and use only those and remove the rest. So to kind of make this clearer, let's look at, okay, before all of that, tokenization. So what is tokenization? So you will, obviously your text will be in sentences, paragraphs, and group of paragraphs, stuff like that. But to work with it, you need to break it down first. And depending on what level you're willing to break down your data, which again depends on what kind of task you're trying to do, we will either break it down into words or break it down into sentences. So in this session, we'll be mainly looking at breaking it down into words and going from there. So essentially, tokenizing is you're given a huge document of text and you're going to break them down into words, a list of words, a Python list of words. So using NLTK's word tokenizer, that's how you tokenize the words. You have a function that's called word underscore tokenizer, and you feed your sentence into it and it will return to you a list of tokens. Over here, tokens refer to words. In general, after tokenization, whatever chunk you get, that chunk will be referred to as a token. So you might be wondering over here, if you've learned this in Python, that Python has a dot split function for strings. So if you're given a string, you might as well do dot split without anything in its arguments, and that would split based on white spaces, right? So have you guys done this in your Python class, the string dot split method?
Yeah,
So yeah, if you do not pass anything to it, it basically needs to split by white space, right?
yeah, yeah,
But we won't prefer or we wouldn't really use that when doing NLP tasks. Now, I'm not going to directly tell you why. I sort of like you to go and research about why that is, why we do not use dot split directly. But we do use word tokenize because it does something differently as compared to dot split. Of course, both of them will give you words because you're splitting based on white space. But as a clue, your dot split will give you something else as well. And you need to find out more about that. So that's sort of a little bit of research work for you to do. Okay. Stop words. So, what are stop words? Okay, so let's look at this with an example. So we have this tweet over here from a Twitter data set. So looking at this tweet, thank you for your quick response. I appreciate your efforts getting me home. It seems to be a positive tweet, right? So you can clearly say that the emotion in this sentence is positive. Now we will remove a few words from this sentence and see what happens. Okay, so now I've removed a few words in between. It just reads thank quick response. Oh shit. Thank quick response. Appreciate efforts getting home. Obviously, that makes no sense, but that's okay. We can still call that tweet positive because even if it doesn't make grammatical or syntactic sense, you can still say that the person or that tweet is telling something positive because it has words like thank, appreciate, and all of that, right? So, in some NLP tasks, you can remove a few connecting words here and there that don't really add information that's relevant to your task. So in this case, it was words like you, I, the, stuff like that. So these words, when you're doing sentiment analysis, they don't particularly convey any emotion. I doesn't convey emotion. The doesn't convey any emotion. This, that, those words don't convey emotions to you. So you don't need that when you're trying to analyze emotion. You only need words like thank you or appreciate, not thank you over here, thank, appreciate, and all of that. Those are the ones that really make the sentence a positive sentence. So these connecting words that you're removing, um, by removing these words, you're not losing information. You might be wondering that, yeah, that sentence makes no sense, and that's why would you remove words like that? It doesn't need to make sense. As long as in your for your task those words do not contribute any information, you can remove them, and you will not have any other effects in removing them. So these connecting words basically that you can sort of chuck out of your sentence, these are called connecting words. I mean, these are called stop words. So if you want to look at an entire list of stop words in English that NLTK has, you can go to this link over here. It will show you the entire list. Few of them being you, I, this, that, again, and all of that. All of those words, they come under stop words because in most situations they're not really giving you more information to the sentence. Like you would not lose information by dropping those words. Even if you're trying to do something like similarity, those words like is, this, conjunction, stuff like that, they appear everywhere, and you if you just do similarity based on that, you will get like a very high score of similarity, which might not actually be indicative of the real similarity. You ideally want to do that on other words that are not very commonly used around.
Your voice is cracking.
uh, oh shit. Okay, is it okay now?
No, it's still a bit. It's still cracking a bit.
Just a second. Is it okay right now?
Yeah, it's better. Yeah.
Okay, cool. Right. So, what was I saying? Yeah. So, even for a task like topic modeling or something, where you're trying to find out what topic a document is talking about, even there, the conjunctions like is, the, and all of those words, they don't really tell you what topic it's talking about, right? So, you might as well remove them, and because they don't convey information to you. And the thing is, if you keep them in and you convert your text into numerical form, you will be unnecessarily using space for something that doesn't really isn't really of much use to you. That is one thing. Second thing is, you might obtain results that are not really indicative of what is that are not really indicative of what you would expect. Like in similarity, maybe you think two documents are pretty different, but you would end up getting a high similarity score if you do not remove words like connecting words that do not really add anything new to your sentence. So, yeah, those words that you can drop
I
without
think your voice
losing.
is still getting cut.
Sorry? Could you repeat your question?
Your voice is getting cut still.
Oh, okay. Just a second. Let me just check.
Mm.
Is it better now? Or is it still cracking?
No, no, it's better now.
Much better. Yeah.
Okay. Right. So, right. So the words that we can drop from a text without losing information about the text, they are called stop words. And you can find a list of those, more of those stop words at this link. All right, moving on. Okay, you have these words over here: working, works, worked. They all are derived from the same root word, that's work, right? So sometimes in NLP, um, you do not want to assign separate vectors or numbers to all of these different forms of the same word, because again, that's like wasting space, because work and working both essentially convey the same information, that there is work being done. It doesn't matter at what point in time it's being done, but the word itself is work, and that's sufficient for our task. So, in most cases of NLP, it also holds not just for verbs, also for nouns. If you have like plural form of nouns like cats or dogs, it doesn't really matter in some or most cases whether it's in the plural form or in the singular form. So you might as well remove the S and make it cat or dog. So that part where you're removing these words, or sorry, the suffix or prefix of words is called stemming. So the suffix or prefix is called the stem, and removing them is called stemming. Lemmetization is a better way actually, or it depends on the context whether you have to do stemming or lemmatization. Lemmatization is also something that deals with trying to bring a verb to its root form, but instead what lemmatization does differently is that it makes sure that the word you end up with is actually a word that you can find in the dictionary. Meanwhile, stemming doesn't always guarantee that. um, so both stemming and lemmatization are used basically to change a verb in its inflected form, which means in either of the tenses, back to its root form. And stemming differs from lemmatization based on the approach it takes. So remember, I was talking about rule-based NLP, right? So stemming is one of those rule-based NLP things. So it uses a bunch of rules to decide how to like cut a word and bring it back to its root form. So it basically tries to remove the suffixes to bring a verb in its inflected forms back to its root form. So even if the word itself, when you like remove its inflection, or if you remove its suffix, sometimes the word might not make sense. For example, if you're talking about a word like making or baking, if you just remove ing, you'll end up with mak or bak, both of which are not real words in the English dictionary. But stemming just leaves it at that. So you will end up with mak or bak. But if your task needs you to have that verb or that word in a proper way, or you want that word to be something that you can find in the dictionary, you better go for lemmatization. Examples would be if you're trying to train a model for question answering. You want your answers to make sense. So, in that way, if you're trying to train a model to answer questions, you wouldn't use stemming, because then or even for summarization, you want the summary to make sense. If you use stemming in these kinds of contexts, you will end up with words that really don't exist in the English dictionary, and that's not what you want in some tasks. Some tasks like sentiment analysis or document similarity is just sufficient that two words that are mapped to the root word are changed to the same thing. So even if mak or bak isn't in the dictionary, as long as making, made, all of this are mapped to the same word, it's fine, because essentially in the end we'll be changing that to some number, and all of these words, as long as they're represented by the same number, we're not losing anything, because in the output you either want to know if it's positive or negative sentiment, or if you're talking about similarity, you want to know how similar two documents are. So you're only dealing with numbers after you pre-process this data. So in cases like that, you can use stemming. In fact, in cases like that, you should use stemming, because stemming is faster than lemmatization. So stemming just removes suffixes and doesn't care if the word is in the dictionary or not. So it's faster because how lemmatization works is it has a lookup table, so it tries to map each word to a proper word in the dictionary. So you have many words and it has to look through the entire table, so it's much slower. So if your task does not require you to have words that make sense in the end, then you are much better off going for stemming rather than lemmatization, because you'll be saving time by doing stemming. Okay, so why we are doing stemming or lemmatization is again because in some cases you really do not need the word to be in its inflected forms to get the information you want. In some cases, it doesn't matter to you in what point in time something happened to be able to tell the sentiment of that verb, like crying. If you're crying now, if you cried yesterday, it still is a negative word. So you do not need the information about the tense to tell which emotion it conveys. And in some cases, like cats or dogs, you like in topic modeling, you do not need it to be in its plural form to tell that it's talking about animals, stuff like that. Okay, so now moving on, regular expressions. So far we've seen tokenizing, and then we've talked about stemming and lemmatization and removing stop words. So sometimes in your data, you have certain words that follow a particular pattern. You either want to retrieve only these words or you want to remove these words. So for example, um, you have a website and you want to retrieve all the emails that might be listed in that website, or maybe you want to retrieve all the phone numbers that you can find in that website. So emails, phone numbers, URLs, all of these, even your SRN that PES gives you, all of these follow like a certain pattern, right? So rather than sitting and trying to hard code something, you can give it, there's a really elegant solution to try and find words that match a particular pattern. This is basically what regular expressions deal with. So in Python, if you want to perform regular expressions, there is a library called RE, which we will be using to perform to match strings that follow a particular pattern. Okay, at this point, I think I like to show you some code of what we were talking about so far. So I will switch to this tab. Okay, so can you see code over here, Python code?
Are you sharing your screen?
Is it
We
not
can't see your
sharing?
screen, I think.
Okay, one sec.
Mhm.
Okay, yeah, now?
Yeah, it's working now. We can see the code.
Yeah. Okay. So this is Collab. Some of you might know what this is. To those of you who don't, it's basically used to code online if you do not have a GPU. So most ML, NLP, and other deep learning tasks, they require a GPU, right? So you do not always have a GPU on your computer. So in that case, you can use Collab. It provides you a free GPU to use on a virtual machine. So yeah, that is what Collab is. And this notebook will also be shared to you after the session. It will be shared as a view only. So if you want to make changes, you'll have to go to File and do Open Notebook in Playground mode. So then you can make changes and run it for yourself basically. So, right. So I was telling NLTK is the most popular toolkit that or Python package that you use for most NLP tasks. So over here, I have done something called nlp.download popular, right? So that's basically to download a few packages that do not directly come with NLTK. So I'll run that once again once. So okay. So if you remember what stop words are, they are the words that do not add much information to our text, right? Over here, I have two tweets taken from a Twitter data set of some airline thing. Okay, I don't really remember where I took it from. So I think it was an airline tweet data set. So we'll try removing the stop words from this. So all of this, the, I, you, and all of that. If you're trying to do sentiment analysis, these words, they don't really convey any emotion to us, do they? Is or I or you, all of these are pretty neutral words. So we do not need those things. So I'll just run this and this. Okay. Word tokenize, if you remember, is to break this word into chunks. So I'll do one thing. I will put the output of one of these things over here. So print sent one underscore token. Yeah. So you can see what it gives as output. Also, an important thing about pre-processing is it's better to convert everything into lowercase. So in this case, stop words are all given in lowercase. So if you're trying to check if a word is a stop word or not, if it's not matching along with the case, it would not be considered a stop word, and we wouldn't want that. So we convert everything into lowercase. If need be, you can bring it back to its original state afterwards, but generally it's preferred to have everything in lowercase before you start with any of your pre-processing tasks. Next, we tokenize it. And okay, in this step, so what stop is equal to stop words dot words does is, I'll do one thing, I print stop also. So it basically returns to you a list of stop words. So NLTK dot corpus has something called stop words, which is a list of stop words, and we pass the language to it as a parameter. So you will get a list of all the stop words in English, and you may not know what this is. This is a list comprehension. It's basically a shorthand way of writing or of adding elements to a list. This is equivalent to writing for w in sent one underscore token, and inside that you have this if condition, and then you do append to this list or something. So this entire one liner is equivalent to that big for loop that you would usually write. So that's something that's called list comprehension in Python. It's just more convenient to write it that way, hence I've written it that way. And over here, this dot join is it's used to join all the elements of either a list, a tuple, or a set. And what you give over here is what it's joined by. So I'm joining all the elements in this sentence, in this list by space. Okay, so let's run this once more because I made changes. Okay, so the first thing I printed was stop, right? So yeah, this is the list of stop words that NLTK has. And second is the output of the tokenizer. So after you tokenize, this is what you get. All the separate words that are separated by white space. And now in this thing, we are removing stop words. So what we are doing over here basically is that if we are iterating over every token we have in our tokenized list, and if that word is not in stop words, only then we will put it in the list, or else we are not putting it in the list. So that's what this if condition is doing, if w not in stop. So if the word is not a stop word, we will append it to this list, else we don't. So these are the tweets without the stop words in them. And as you can see, it's still you still can tell the emotion behind them. Like this one, clearly it's not really positive because it has worst. I mean, it's not really anything if it didn't have worst, but it does have worst, so we can say it's negative. And this one, like I showed you, or rather I was telling you when I was explaining, is positive. Okay, so next, I was talking about stemming, and stemming basically, I said it will remove, it's rule based, so it just follows a bunch of rules. It's sort of brute force, so it just removes these suffixes ed, ing, es, and stuff like that. So in stemming, you have two stemmers. Porter stemmer is the one that's most frequently used. The other stemmer, Lancaster stemmer, it has a tendency of overstemming. So it'll cut down your word too much and it will make no sense at all. So, and it's also in general not used a lot. So Porter stemma is the kind of stemma that's usually used in most stemming tasks. So let's run this and see the output. Okay, so for dogs, it remove the s because, like I was saying, it brings it back to its root form. So if something is in its plural state, it brings it to its singular state. And rambling, it should actually be ramble, right? So that's the word ramble. But like I said, since it's rule based, it doesn't really care if ramble is a word in the English dictionary. It just removes the suffixes and it just throws it out. So that's stemming. Also, important thing about stemming is that it expects its parameter to be a word. So if you're passing in an entire string like this, it will not do anything to it because it doesn't know what to do with a string like that. So it expects a word. So you see, this was a sentence, the entire sentence I passed to the stemmer, and the thing was, it just remained as it is. Also, another thing that I forgot to talk about is this line. So basically, this line is initializing an object. So Porter stemma object, you're initializing that in this line, and it has a function that's called stem. These words make no sense to you, it's fine. You don't have to understand all of that at this point in time. But basically, this is initializing an object, and that object is trying to perform the function of stemming. That's what it is. Moving on to lemmatization. So, like I was saying, lemmatization also is concerned with bringing a word back to its root form, but it makes sure that the word actually exists. So, over here you can see that when it was run on the same input as the stemmer gave a word that doesn't exist in the dictionary because it simply removed the suffix. By contrast, the lemmatizer actually gave you ramble, the correct word. Um, so if your task requires you to have the words in their like proper meaningful form, go for lemmatizer or else go for stemmer. But word of caution is that lemmatizer is slower. So if unless absolutely necessary, you do not need to go for a lemmatizer. Also, you might be wondering what this is. POS is equal to V. So POS stands for part of speech, and if you remember, I was saying a part of speech denotes if a word is a verb, a noun, an adverb, or something like that. So if you do not pass this term to your lemmatizer, it considers by default every word that you pass to it, it thinks it's a noun. So it tries to lemmatize it or bring it to its root form, thinking it's a noun. But in this case, it's a verb. So I'm explicitly telling it that over here V stands for verb. So I'm explicitly telling Lemmatizer that it's a verb and you have to bring it to its root form like you would do for a verb. Okay, so I showed you that this doesn't work. And right, so for anything, either the Lemmatizer or for the stemmer to work, first you need to, if you want to perform that on an entire sentence, you first need to break the sentence down to its tokens and then iterate over each token to lemmatize the word and put that back into another list. So that is the same with stemming. So both of these things, they take an input as a string, but if you pass your entire sentence as that string, you won't get what you want, what you expect you would. So like I showed you before, you pass this entire sentence to the stemmer, it just throws out the same sentence back. So remember that it must always be a word and not a sentence. Okay, so regular expressions, right? So before I get into this, I think I'll talk a little bit more. Okay, right. Okay, so some more basics about regular expressions. So this is basically kind of the syntax you need to follow while trying to frame a regular expression for something. So this caret symbol, this is called a caret, it denotes the beginning of the string. So for instance, if you're trying to search for words that begin with an A, you would use this symbol in front of the in front of whatever you're trying to search, in front of whatever should be the beginning of what you're trying to search. Dollar, the same way, it indicates the end of a string. So if you want your string to be something that's ending with an ing, you do $ing. And this vertical line, it's basically the OR operation for regex. So if you want something like, I want my string to contain either A or B, so you do A and that vertical line and B. And square brackets, within the square brackets, whatever you specify is the set of characters that the regex will try to match. So for example, if you have square bracket ABC, then any string that has either A or B or C will match your regex. So you can also specify ranges in the same format. You just need to use a hyphen in between. So A hyphen E will match anything from A to E, and it's the same as A, B, C, D, E. And 1 to 4 will be 1, 2, 3, 4. Right. So in a similar way, this thing 0 to 9. Okay, so if you use a caret inside the square brackets, it's a complement. So anything except 0 to 9 will be matched with your regex. So caret normally is the beginning of the string, but when used inside the square brackets, it means that you're trying to complement whatever is there in the square brackets. So except 0 to 9 is any non-digit character. Any non-digit character will get matched with this. A period, by which I mean a dot. A dot will match any character except a new line character. So it's like a wild card basically. So any character you want, you can use a dot and it will match it. So an example would be if you're trying to match it with either a alphabet or a number or a special character, or if it's any character at all that you're expecting your string to have, a period will match with that. A star is used, God, a star is used when you have when you are supposed to match either zero occurrences or more than zero occurrences. So minimum, so it's sort of like it can be 0 or more than 0 when you're using a star. And by contrast, a plus means that it must be at least one or more occurrences. In a flower bracket, n comma n means that you're matching uh, at least n or at most m repetitions of the pattern. So if you do something like a flower bracket 1 comma 8, so you're trying to match at least 1a or maximum of 8 a's. So it's so everything in between is also there. So 2 a's, 3 a's, everything. At most it's 8, at least it's 1. So as you can probably tell, if you have a flower bracket and 1 comma with nothing else as m, that would be equivalent to your plus operator. If you have your flower bracket and you have a star, comma, and nothing else after that, that is, if you have 0, comma, nothing else after that, that is equivalent to your star operator. So these two are pretty generic and this is more specific. So suppose you want your minimum number to be 3 and maximum can be 100. So you can do flower bracket 3, comma 100. Let's take an example to sort of understand this better. Over here, the example I've taken is that of an email. So typically an email will be some set of characters followed by an ampersand, followed by the site name, then a dot, and then a domain name like .com, .org, stuff like that, right? So the first is some set of characters. So this square brackets is the set of characters. So over here, it's it is A to Z, small case or small letters, capital A to Z, 0 to 9, because it can be any character, right? So you can also use the wildcard over here. It's also valid. You can use the wildcard over here. The dot operator I was talking about. It can be any character. So uh, or can it? I don't think it can be characters other than these special characters, right? So maybe you cannot use dot actually over this. So it needs to be either a letter or a number or either of these special characters, underscore or plus or minus, stuff like that. So this plus after the square brackets indicates that either one or more occurrences of any of these things that is listed over here. So either one or more occurrences of small letters or capital letters or numbers or special characters. So this is followed by the ampersand symbol. So we put the ampersand straight away beside it. So you don't need to do anything like put a comma or anything. It's just keep continuing whatever you want. Followed by the website name. The website name again can be another set of characters, um, except for the special characters, of course. So that is also, it can be one or more small letters, capital letters, numbers, and so on. So now .com, right? So we need a dot. But like I told you before, dot has a special meaning for regex. It's the wildcard operator. So I do not want it to go with that meaning. I want it to take the actual literal meaning of a dot. I do not want it to match with any character. I want it to match with the dot. So in that case, I'll have to precede that dot by a backslash to sort of tell that this is not the special meaning that it is to you. It is just the dot that I want to match. So finally, the domain name. So the domain name is also again more set of characters. So it is also in the same format over here. So now let's actually see the code I've written for this. So this doesn't really work, does it, when I say share this tab instead? Okay, never mind. Yeah. So over here I have this string that has males in it. So yeah, it has this as a male. This is a male ID and this is also a male ID. So essentially the output of this should be xyz at ps.edu on the HOD's mail and my mail ID. So let's just run this and see if it's okay. So like I was telling, RE is the package that you use in Python to perform operations related to regular expressions. So find all is used to find all matching instances that match with this given regex. So the regex that I showed you in the PPT, it's the same thing. So find all will give you a list of everything in this text that matches with this regex. And I'm just iterating to that list to print it out neatly, sort of. So yeah, let's just run it. So as you can see, it has given you the output that you were expecting. That is this, and this. Right, so like I said, this notebook will be given to you. You can probably try it out for other kind of strings or other, if you're trying to match something else, you could try it for your SRNs maybe, or actually I have like a list of stuff you could try out after this session, so we'll talk more about that then. Right. Okay, so any questions so far? So I think I've been pretty much in a monologue for quite some time. So does anybody have any questions?
Yeah, one thing, I
Yeah.
think you said this before. I don't know if I could hear it before, but how would you match like a specific number of characters? For example, you just like you want to search that if it has if a phrase has only three A's or six B's. So how do you
Okay,
specify
so
that?
only three A's, right? So
Yeah.
you go for like the flower bracket, but instead of M, you just put a flower bracket 3. So you do A flower bracket 3.
Okay. Okay. Yeah. Thanks.
Any other questions? Okay, I'm assuming that's a no. Or
What if you don't give any value for M?
what if you do not? Yeah, like I was saying, there are two cases where you wouldn't give a value for M. If you're trying to match a specific number, like you said, 3 A's, so you'd just do flower bracket
Okay.
3. Or
Okay.
if you do 3 comma, then it's 3 or more. That's what it means. So just leaving that out
Oh,
is
okay.
basically equivalent to saying infinity. So
Okay.
that's
Right.
how
Right.
1 comma is equivalent to plus, because it matches at least one and at most how many ever.
Yeah. Yeah. Okay.
You will
Thank
have
you.
more about regex again in your automata course. That you probably have in your third sem. All of this will come again. So, yeah. Any other questions? I I don't know if have I been going too fast. I do have a habit of sort of rambling once I start talking about stuff. So if I'm going too fast, please do let me know. I do have a tendency of just sort of rambling in a monologue. So I'm assuming you don't have any more questions. So we'll go on to the last part of this session then. So that's before going on to bag of words, let's talk a bit about text vectorization. There are many methods actually for text vectorization. Bag of words is the most simple one of them. So basically, text vectorization is converting your words into numbers. You can intuitively, if you're given like a bunch of text, how would you try to convert it into numbers? Any guesses? It's okay, it doesn't need to be right. How would you go about trying to convert it into numbers if you're given like a huge text, a document of text? On what basis do you think we should convert it into numbers?
ASCII.
ASCII is not a bad answer because it does map characters to numbers. But the thing with ASCII is that it doesn't always give you the meaning, right? So if you have like two words that have the same set of characters, they'll be mapped to the same set of numbers. And sometimes just because two words have the same characters doesn't necessarily mean they are related in any way. So, though ASCII is a way of converting text to numbers, um, something that I would say is intuitive, that's not too complicated, is trying to count the frequency of each word. So, basically you tokenize your words, which is splitting them, I mean tokenize your text, sorry, splitting them into words, and then for each word you see how many times it's been used in the document. So you're sort of mapping the word with its frequency. So it makes sense for some tasks. Okay, so if you're doing something like topic modeling or summary, so if you're trying to find out which is the most important topic in your document, so then you would say something that's appearing more frequently is somewhat more important, or that's the recurring theme in your document, right? Because it has a higher frequency. Um, Also, if you're trying to do sentiment analysis, you try to see that in tweets that are labeled as negative. So usually when you're doing sentiment analysis, you'll have one column having the tweet and the other column having saying whether the tweet is a positive sentiment or a negative sentiment. So you can sort of do something like based on how many times a certain word is used, you can decide that, okay, if it's a negative tweet, then this word will be used pretty frequently, like angry or sad, that those words are more frequently used in negative tweets. So, word frequency is not a bad way of trying to convert your text into a number form, a numerical form. So that's exactly what bag of words does. So it tries to map every word that you have with its frequency. Now, why is it called a bag of words? It's called a bag because you're just throwing in the words. You do not care much about the order in which they're appearing. So suppose I say, this is my house, and you just convert them into tokens and you just throw them into your matrix. You do not really care whether this comes first or is comes first. You just maybe sort of sometimes people sort them in alphabetical order, or usually you sort them in alphabetical order, and then you try to map each word with the frequency that it appeared in the document. So it's basically called back because it doesn't take order into consideration, and you're just sort of mapping it with only the frequency. And in mathematics, it's called a multi-set of words, and in math, multi-set is sort of like a set, but it allows multiple instances. So you might know that a set, you can only have one instance of an element in it, but a multi-set is a slight modification on that. You can have multiple instances of the same element. Okay, so another really important term over here is something that's called a document term matrix. So, what is a document term matrix? Basically, you have a matrix that in whose rows represent each of your documents. So, suppose you're given like a list of documents. So, and you're given the task of converting these documents to its numerical form. So, what you would do in the document term matrix representation is each row for you would be each document, and next you would try to find out the unique words that occur in all of your documents put together. So you're going to find out all the unique words that your document has. And each of these unique rows will form the columns of your document term matrix. And what are the elements? The elements, so you will form like sort of a crisscross, right? Let me actually go further. Okay, so this is an example of a document term matrix. So this element represents how many times this word has occurred in this document. So this is what a document term matrix looks like. This is one of the ways of converting your raw text into its numerical form. So most ML algorithms, they work with matrices or vectors. So this is what we do to convert this raw text into a vector or a matrix. Right, so let's go back again. Okay, so this example, we have for a minute, let's consider each of these sentences to be separate documents, okay? Because each document would be larger than this, but for this example, let's consider sentences. And the first sentence is many people love dogs and cats. Second sentence is I love dogs. Third sentence is I'm scared of cats. So first step would be to tokenize these sentences. So like I was saying, this is your pre-processing step. Actually, you could also first convert everything to lowercase. That is the first thing that you probably could do even before tokenizing your text. But over here I haven't. So let's just tokenize the text, break them down into words, because in this or in this situation we're working with word frequency, so we want them as separate words. So we get like 3 lists of the separate tokens that you have in each sentence. Next, we will find the unique words in all of these sentences. So you can see some words were repeated across these sentences like love or dogs and cats too. So I don't want to use these words again and again in this column. So it wouldn't be of any use to have love twice or dog twice, because you're just trying to find out how many times this word has occurred in this document. So we need to make a unique list, or make a list of all the unique words in across all of your documents. Now this set that you get that has all the unique words is called a vocabulary. In Python, quite literally, you take the entire list of words that you get from all of your documents and pass it through a set and change it back to a list that will have only the unique words, that only words that or rather I should say only one entry for each word. Even if they're repetitions, you'll have only one entry of that word. So now, like I was saying, once you have your vocabulary ready, so each row represents your document. And like I said, in this example, each sentence is a document for us. So many people love dogs and cats is the first document. So many occurs once in that sentence, people occurs once in that sentence, love occurs once, dogs occurs once, and occurs once, cats occurs once. I am scared of all of these words do not occur at all in your first document. In your second document, that is I love dogs, So you do not have any occurrence of the word many, any occurrence of the word people. You do have one occurrence of the word love, have one occurrence of dogs, none of and, none of cats, and none of the other ones. And for the last one, which is I am scared of cats, you have one occurrence of cats and everything else, and none of these. So basically, that's what your bag of words representation is. This is the simplest algorithm that's used to convert your textual data into a numerical form. Now, there are many drawbacks of using a bag of word model. I'll talk a little bit more about that at the end of this session, but yeah. Okay, before this, so let's just look at how we could code the bag of words algorithm. So let me just go back to the collab. Yeah. Okay, so this is the bag of words model. So these are the strings, okay? So I've hard coded them. You don't need to hard code them. You can read them from a file using file operations if that's done for you or if you know how to do it. So these are the sentences, or in this case, let's consider each sentence to be a document because a document would be too big to represent like this. So first step, we need to do the pre-processing that we talked about today. So I'm going to lower each word because like I said, if you want to do removing stop words, the stop words will be in lowercase as well. So if you're trying to compare them, it will compare along with case, and you want all of the stop words to be removed. So it's better you convert all of your words to lowercase before you do any other pre-processing task. And you can tokenize it beforehand, that's fine, because tokenizing doesn't really depend on case. So tokenizing, basically this would give you the list of words like I showed you before. So if you do word underscore tokenize and pass a sentence to it, the output would be the list of the individual words in that sentence. This again is a list comprehension. This is equivalent to writing for W in words, append to lower dot append W dot lower. So that's what it's equivalent to. In case that's kind of hard to understand me just saying code, I'll just put it in comments over here. So that basically is equivalent to for W in words and L dot, or what was it, lower dot append W dot lower. So this entire one liner is the same as this thing. Okay, so is this convenient to write it in this way? If it is confusing to you, you can expand and write it in its for loop equivalent all the time, even in the examples I showed you before. Okay, so next, we are stemming the words because depending upon your, like I was telling you when we were talking about stemming or lemmatization, depending on what your task is, finally, eventually, you do not need the tense or the form or the any of the higher forms of the word. You just need the root form. So in this case, I'm not trying to do any task after this, but suppose imagine we're trying to do sentiment analysis. So for that, it doesn't really matter the tense of the word or if it's in plural or singular. It doesn't really matter when you're trying to do sentiment analysis. So for this case, it doesn't matter. And for this case, the meaning doesn't matter either. So I do not need the stemmed words to make sense, because in the end, if they're all chucked into the same or mapped to the same number, it's fine, because at the end we are all dealing with numbers and the words need not make sense. Okay, so that's what I'm doing over here. Again, this is a list comprehension. If it's too complex, let me just write down the for loop equivalent for this as well. So for W in lower, basically what you're doing is, let's just say stemmed is equal to porter dot stem W, and Okay, before this, I'm checking if W is not a stop word. If W, if not W in stop. Okay, and also and. So and W dot is alpha. Wait, was that too many brackets? No, it wasn't. Okay. And this needs to be indented and okay, so basically the entire thing I'd written over here, this one line, is equivalent to this for loop. So if it's confusing for you to look at it in this way, just write it down in this way. It's the same thing. So the next thing that we're doing, so next in our algorithm is to get our vocabulary, which is the unique words in our documents, right? Across all documents. So for that, first I'm going to tokenize the entire, all of the sentences. So the input to this would be the list of your sentences. Over here it's sentences, typically it's the list of your documents. So we're going to iterate through each of these sentences and tokenize each one of them. Clean tokenize was this function that I defined over here. It removes stop words as well, so and stems them. So what this does is it appends to, it makes a list of all the words that are not stop words and that are stemmed. So now we are going to iterate through this list and append them in a larger list called vocab, because what you get over here is a list, and if you directly append that to vocab, you'll get a list of lists, and then you'll have to again sort of expand that to make it a, or flatten that out to sort of make it into just a list instead of list of lists. So since this is a list, and if you append it directly to vocab without this for condition, you'll get a list of lists, which we do not want. So like I was saying, in Python, you just need to pass the list through set in order for you to remove duplicate elements. So that's a handy way of removing duplicate elements in Python. So before doing that though, I'm sorting it alphabetically. So because it's always easier or it's convenient to have it sorted in some way. Because when you're trying to like access the data, if it's not sorted, then you'll have to keep track of what each column corresponds to as well. If it's sorted, you know it's in alphabetical order, so it's easy access. That's why I'm sorting it first, then removing duplicates by making it a set, and then I'd like it to be in a list, so I'm just making it back to a list. So next is making the bag of words itself. If you remember, after making our vocabulary, what we need to do is we need to go through the go through each of your documents and check how many times each word in your vocabulary has occurred in that document. So basically, first I'm going to get the vocabulary, then tokenizing all of my sentences. I'm going to tokenize and clean them in the same step over here. So basically clean tokenize, it's removing stop words, stemming words, tokenizing them. And this is a list of lists. This is a list of lists. So it has something like A, B, stuff like this. Oh, God. B, and so it is a list of the individual tokens in each of your sentences, the output of that. Actually, I can print that out as well so that it's easy to understand. So let's print that out as well. Right. So then eventually we need to put all of these in a matrix. So that's what I'm keeping this matrix for. So now we have a list like this, right? So what we're doing is we're iterating through each of these lists. So that is TS and token sense. For V in vocab, so we are using this for loop to iterate through our vocabulary. So for each word, for each document, we are checking each word in the vocabulary if the count of the number of times it occurs in this document. So suppose our vocabulary also started with an A, and our document starts with it, and our document has one A. So it'll append to vector 1. Vector over here is used to store each row of this matrix. So I'm going to append everything to different vectors, and then I'm going to, if you observe for like each document, I'm reinitializing vector. So vector is basically something um, in the final matrix, each row is a vector. So this A will be replaced by a 1 in its vector equivalent, and the matrix will be this entire thing, a list of lists basically. So to make it easier to understand, I guess I'll print this out as well once. So ts.count, so list.count is a function that is used to count the number of occurrences of this v in this list. So ts is a list like this. So a comma b is ts, and we are counting the number of occurrences of this this word in the vocabulary in the list. So that's what this statement is doing. And after counting that, we're going to append it to our final matrix. So we're going to append each row to the matrix. So I'm going to print vector over here so you can see. Okay, so over here I'm converting this list of lists to an NP array, NumPy array. So there's a reason why I'm doing this. This is because you can leave it out as a list of lists, there's no issue. But the thing is, it's slow, it's pretty slow iterating over a list of lists. NumPy will give you that it is faster to use NumPy arrays or when you're doing ML or DL related tasks. This is because NumPy, first of all, is based on C, and C is faster than Python. And secondly, NumPy uses something that's called vectorization. So it uses something called single instruction, multiple data. So what it does is it executes a task on more than one element. So if you iterated over a list of lists, you would go element by element. But if you use an NP array, suppose you're adding two arrays or multiplying two arrays, it takes more than one element at a time, a chunk, a group of elements, and it performs the operation. So that is vectorization. So it's faster to use an array, and in general, in most ML related stuff, you preferably do not use lists. You use arrays, NumPy arrays instead, because we want it to be as fast as possible. Right, so that's a lot of talking. Let's just run this once. Okay, so the first thing that I printed out, what was it? What was the first thing that I printed? Okay, yeah, the vocabulary. Was it the vocabulary? This not. Yeah. Okay. So this is the vocabulary. As you can see, this is the result of the stemmer not being able to the stemmer just trying to stem many, and it just gave you a word that isn't really a part of the dictionary. So that's why you get words like that if you use stemmer. And like I said, if you do not want that to happen, use a lemmetizer instead. So I printed vector, right? Yeah. Okay, so actually I should have printed that outside the for loop. Never mind. Yeah. So each of these rows is the vector, as you can see over here. This row is each of the rows of the matrix is a vector. So I hope you understood what this vector really is. It's just iterating through this sentence by sentence, and the vector is the numerical representation of this document, and the second vector is the numerical representation of this document. And by numerical representation, I mean each word in this document is mapped to its frequency. So over here, many is occurring once in the first sentence, so you get one over here. And what was the next thing? Okay, this is alphabetical order, I forgot. Yeah, so we made the columns alphabetical order, right? Because if you remember, the vocabulary was sorted before I made it into a set. So the first column over here corresponds to and the next column corresponds to cat, and the next to dog. So in the first sentence you have one and, so you have one over here. Let me just show you the first sentence once again. First sentence is many people love dogs and cats. So the first sentence has an and, so one and, so you have one over here. And the second, what was the second word though? Okay, let me just print the vocab. Have I not printed vocab? This is the vocab. Okay, wait. So each column represents one word from the vocab. So this is the vocabulary that we have over here. Since I made it back into a list, it's not in order anymore. So I probably should remove that list from this thing. Where was that statement? Okay. Yeah. If I remove list, let it just be set. That will keep it in order. So the thing is, when you convert a Python set back to a list, it won't be in order anymore. So if you want it to be in order, so what? Unexpected indented clean. Okay, let me just. So the thing with Python is when you convert a list to a set, the order is different. So there's no point in trying to sort this. So we just convert it into a set, and then we convert this into a list, and then we sort this thing. Right. So let's just go back here and hopefully this thing changes now. Okay, yeah. Yeah, and is a stopword, so and doesn't exist. Fine. So this is the vocabulary. Now it's sorted. So now the first sentence has one occurrence of cat, one occurrence of dog, no occurrence of friend. So you can look through it later. So it's kind of tricky to just keep seeing this. So yeah, many people love dogs and cats is the first sentence. So it has no occurrence of friend, no occurrence of hate. It has one occurrence of love, one occurrence of many, one occurrence of people, none of scare, none of those. So each row over here represents each document, in this case each sentence, and yeah, that is the bag of words representation essentially. So with that, we've come to the end of this session. So if you have any questions about bag of words or anything at all, feel free to ask right now. Any questions?
Could you just tell again, like when to use stemming and when to use lemmatization?
Okay, so suppose you're trying to summarize text, and for that, sometimes in summary, you're trying to put everything in the same tense, or um, for summarization, you do not, or you need your words to make sense, right, in the end. So if you do stemming, it might get mapped to a word that doesn't exist. So for a word like making, stemming will just remove ing and you'll be left with mak, which isn't a real word. So if you're using that word again in some other way, like a output, for a summarization thing, you will be using all of your words again in the final summary, right? So if you have mak in your summary, it doesn't really make any sense. So for cases like that, where you will be using your words again somewhere, do not do stemming. Lemmetization would work better for that. Or to be exact about this, for models, when you're trying to train a model, specifically like a neural network, suppose, those things you can train like a Q&A model or a generating model. You can pass in a stemmed or lemmatized version in order to cut down on your memory requirements, because mapping every form of a word will just increase your memory consumption. But if the output of the model is text again, so the model learns whatever it takes in as input. So if you're giving it stemmed words as input, it will give you stemmed words as output for a language generation task or a question answering task. So for things like that, where you're generating natural language again, you do not want stem words to appear because they're not natural language. They do not make sense. They do not appear in the dictionary. By contrast, for something like sentiment analysis or document similarity, what happens is, even though your making and all is changed to MAK, every occurrence of making or any other form of make will also be changed to MAK, right? So finally, you will be counting the frequency of MAK only, and you'll be replacing MAK with its frequency. And then you will be trying to do sentiment analysis or document similarity. All of these tasks, they just deal with the numbers, and in no other way are you going to give language again as output. You're only going to give, well, either it's a positive sentiment or negative or the similarity, stuff like this, but you're not generating language again. In these contexts, it's okay to use stemming. In fact, it's preferable to use stemming because stemming is faster. I hope that answered your question.
Yeah, I got it. Thanks.
So basically, stemming is useful for matrix generation.
Yeah, basically, if you're only going to be working with the numbers and you're not looking to convert text from one form to another, then it's fine. You can use stemming. In fact, it's better you use stemming. If your output contains words again, so if you're making a model that generates language, then you can use lemmatization if you want to cut down on memory requirements, but not stemming, because if you feed it words that don't make sense, it will also generate the same things because that's what it was taught. So it's kind of intuitively I'm explaining this. It's DL related stuff, but it's okay. Intuitively, a
Yeah,
machine,
it makes sense. It makes
yeah.
sense right now.
So that's where you'd probably use lemmatization. Where your output is also some form of natural language, then you'd probably use lemmatization. Any other questions?
So you are using Google Colab, right, for
Yeah,
running your programs.
yeah,
Is that like completely free?
yeah, it's free. I mean,
There's no
it
like time
does
limit.
have a few limitations. Yes, it you can only use it for a while before it disconnects, and if you overuse it, it does like stop you from using it for a while till you can. It makes you wait before you can use it again. So it does have
Oh,
limitations, yes, but it's pretty convenient to use for like small to medium scale MLDL tasks, because not everybody will have powerful GPUs. So Colab is pretty good for that.
okay.
But yeah, for it's free. You can use it for free. I'm using it for free only. Any other questions? The collab will be shared to you, so will the PPT in case you want. If there aren't any questions, then I'd like to just show you one last thing before we end today's session. So,
Yeah,
right.
sure.
Okay, the last thing. So, based on everything that we've learned today, so there's some stuff that you can try. I understand that online classes are pretty hectic and it'll be pretty challenging to make time, but if you do have time, you can try some of these things out. So, like I was saying, one of the utilities of NLTK, or one of its positives, is that it provides a lot of corpora you can work with. So one of them is the Twitter samples one. So the way you import it to use it in your programs is like given over here. So it's actually a JSON file, so you need to do dot strings to convert it into strings. So finally you'll be given a list of tweets. And with this list of tweets, there you can practice some of the things that we've done in today's session. So you can perform all the pre-processing techniques that you learned. You can tokenize, remove stop words. You can practice few regex expressions, like try removing the URLs in the tweets, because mostly, for most tasks, you wouldn't really need the URLs in the tweet. Try to remove the at usernames. This is pretty simple. It's just you need to make sure the string starts with an at, right? So at usernames. And finally, you can try and convert the first few tweets into its bag of words representation. It's a pretty nice starting point for you to get into any other kind of NLP tasks. So, as a continuation of this session, in the next session, we'll be looking at a better way to vectorize text.